Good afternoon. Can you hear my voice? Okay. During the last session, we start to talk about network security, and we start to talk about cryptography as one of the basics of network security tools. And we said that even if an attacker knows our strategy or cryptography strategy, he or she can try to break or ciphertext. We talked about this a little, but let me continue the course with talking about symmetric key cryptography. What is symmetric cryptography? When we talked about cryptography, we have two different ideas. The first one is using a symmetric key for encrypting and decrypting a text, plain text, for example. Excuse me. Oh, yes, sir. Okay. So I'm repeating again. In your home, you have a key. Then you can go and create some other copy of your key. For example, you can have a key. You can get a key to your parents, your wife, your husband, your kids. Okay, you can give them their copies. So you can lock the door and they can unlock the door. This strategy is symmetric key strategy. In cryptography, we have a similar strategy. We have a symmetric key or K of S. So Alice can encrypt her plain text by the symmetric key, and the ciphertext encrypted by the symmetric key then can be sent over the network. At the receiver, the Bob can decrypt the key, can decrypt the ciphertext using the symmetric key again. Okay, he can decrypt the text and extract the plain text from the received message. So when we are talking about a symmetric key cryptography, it means that Bob and Alice use a shared key. There is one key, and Bob and Alice can have their copies of that key. So who is Bob and who is Alice? I don't know. Everyone who has the key can encrypt the message or can decrypt the message. This is the main problem with the symmetric key cryptography. Each person who has the key. And there is another question too. Okay, Bob and Alice are using a symmetric cryptography, but how they can agree with the key value? Their key must have a value, okay? So how they agree with the value of that key? How? Here we don't talk about the strategy of cryptography, basics of the algorithm, a specific algorithm, okay? We are talking generally. symmetric key cryptography. For example, we can have several techniques when we talk about cryptography. For example, when we talked about asymmetric key cryptography, we can use, for example, substitution ciphering. What is this? In this strategy, for example, here, look at this one. Here we have different characters, English characters, okay, and we then just we substitute those characters with someone else. Okay, for example, instead of A, we can use M. Instead of B, we can use N. Or for example, instead of Z, we can use Q. So if I have this plain text, Bob, I love you, Alice. Okay. According to this key here, to these strategies for substitution, here, instead of B, I know that I should use N. So N, we have two B's, two B characters here. So I'm replacing those B with N. Instead of O, I should use K. So here, this O is replaced by K, here again, and here again. Instead of I, I'm replacing it with S. I-S. Instead of L, we are using G. Okay? Just we substitute each character by a new one. How? Based on this strategy here. This is the key. This is all key for substitution, all key for encryption. We are replacing one character by another one. Here we have in English, we have a set of 26 different characters. Those characters are replaced by someone else in substitution ciphering, and this is the key. But this is said in this strategy can be breaked. We can break it very easy. How? For example, in English, I know that we are starting with, for example, this letter can be started with I. I is a single character, and so statistically, I can recover this. For example, I can replace I when I see S, I can replace it with I. Or I know that this message is sent between Bob and Alice. So NKN maybe is Bob, and MGSBC maybe is Alice. Maybe, I don't know. Okay. So if my idea about the substituted characters is correct, I can find those replaced characters, and I can continue this strategy. Okay. So this strategy can be breaked easily. We have another strategy. Instead of using one substitution key or one substitution ciphering, I can use n different substitution ciphers. We are showing them by M1, M2 until mn, m of n, okay? And then I can use a cycling pattern here. I have n different patterns, okay? And then I can use a cycling pattern. What does it mean? For example, here, n is equal to 4. So it means I have 4 different patterns. And then for the first character, I'm using pattern M1. For the second character, I'm using pattern M3. For the third character, I'm using pattern M4. For the fourth one, M3. For the fifth one, M2. You know, for each character, I'm using a specific substitution cipher. And I know that that is substitution cipher is different from the others. So one by one, character by character, I'm using different strategies. And when we say that this pattern is cycling, it means that I'm continuing this strategy M1, M3, M4, M3, M2, and again M1, M3, M4, M3, M2. And we continue, we repeat this strategy. So we call it a cycling pattern. This pattern is recycled during the work. And for each character, I should find, okay, this character should be replaced by the ciphertext, for example, ciphertext X. Okay? So if you use this strategy, its breaking is a little hard. So for each, because for each character, I'm using another characters. For example, let's see this example. We receive a word dog. Okay, this word has D, O, and G letters, characters. Okay, according to this pattern, D. If I want to replace D, I should look for D in pattern M1. For O, I should look for O in pattern M3, and for G, I should look in pattern M4. Each pattern has a specific string of characters. I should look on those patterns and replace the word dog here. So this strategy is more sophisticated than using a single substitution cipher. There is another algorithm for encryption. Its name is DES, or data encryption standard. This standard is used more than 3 decades, but in 1993, the NIST organization tried to standard this algorithm, the DES algorithm. The DES algorithm is using 56-bit symmetry key and 64-bit plain text inputs. Okay. This strategy, this is consists of 16 different steps. In each of those steps, we try to encrypt the message, to encrypt, replace, and enhance the message during each of those 16 steps. Okay. But it's very interesting that this algorithm with 16 different steps, those steps, if you look on inside this, you can see that in each step we have some shift to right or left. We have some XOR operation and several other operations during each of those steps. But today we know that this codes can be decrypted very easy in a few minutes. Why? What is the problem with this? The problem is that this uses small keys. Here we say that the symmetric key is 56-bit key. Is a 56-bit key. Okay, this length is too short for decryption. This key is very short. Why? I don't know why, but if you use brute force attacks, you can decrypt or break this encryption strategy very soon, just in a few hours, maybe in a few minutes. Okay, Naima, I will answer your questions. Okay, so how can I overcome this problem? We have another strategy, comes from this. We call it triple this. Triple this means that I'm repeating the encryption of this strategy 3 times. So we have 3 56-bit keys. Wait a minute, I will be back very soon. For this, we are using this mechanism, this strategy, this algorithm 3 times. So we can use 3 different keys because I'm using this triple times. So 3 times. So we can use 3 different keys, or maybe we can use 2 different keys. How? During the first step, I'm using, for example, key number 1. In the second round, I'm using key number 2, and in the third round, I'm using key number 1. So in triple this, we need 3 different keys, but we can reduce them into 2 different keys. But generally speaking, in this case, we are using 3 keys with 168 bits. So triple this is very strong. If I compare it with, for example, this, we can break this easily, but In triple this, we cannot break it easily. But after the weakness of this, in the USA, another encryption standard has been proposed. Its name is AES, or Advanced Encryption Standard. This standard is proposed in November 2001 by the NIST organization, again, NIST, to replace this strategy. The AES standard is using blocks of data with 128-bit length, and in this standard, I can use the keys with 128, 192, or 256-bit length. So you can see, comparing with this, in AES we are using larger keys. Using larger keys means means that AES is stronger than this strategy. To compare this strength, I can use, for example, I can say that, for example, let's suppose that I am finding I'm decrypting the texts which are encrypted with this in 1 second. It means that I'm spending 1 second to decrypt this encrypted text. If I spend only 1 second, in this case, only 1 second to find the encrypted message in this, with similar specifications in our computing platforms, we should spend 149 trillion of years to decrypt AES messages, AES encrypted messages. It's very good. This is strong, but we know that this strong algorithm can be replaced very easily. They can be break easily. But here we can see that if this needs only 1 second to decrypt the message, for AES we need to 49 trillion dollars, trillion years to decrypt the texts which are encrypted by AES. This shows the strength and the amount of strength in AES strategy. Okay. Yes. By using brute force attacks, we can decrypt these messages, these encrypted messages, very easily. But in comparison, we need to spend too many years to decrypt a similar text which is encrypted by AES. Okay. Okay. As I said, when we talked about encryption, we have two different strategies. The first one is using symmetric keys, but the main question is this: how we can share that key? Because we know that if someone else receives that key, he or she can enter the sending software.